So looking at this particular theorem 2.3, which is polynomials acted upon matrices, the proof is well stated here, such that you have A, which is an n by n matrix with a corresponding eigenvalues of lambda 1, lambda up to lambda n, including their multiplicity. You also have a g of x, which is equals to a polynomial g of x, which is given as thus, and a polynomial g, which is in terms of a. Instead of using x this time around, now we have it substituted as what? As a matrix. Okay, it's a matrix format. But whatever I want you to take note here is that the proof are well stated for the theorem 2.1 and for the theorem 2.4 and also for the theorem 2.6, the product. You don't really need to explain this. You don't really need to show the proof for them in this case. Whatever you have to do here is that, okay, we have the algorithm as it was said earlier. The algorithm for this method is that we need to set up, the first step is to set up a characteristics equation. A characteristics equation of this format, which is A minus lambda I equals to 0. This A must be must be a square matrix. If you have a square matrix of, let's say, 2 1 minus 1 4 minus lambda, I simply implies an identity matrix. If I use this matrix to be 2 by 2, automatically speaking, the I must correspond to this dimension also. It must be 2 by 2 matrix. This identity matrix of 2 by 2 is always given as 1 in a diagonal part, and then you feed the rest with 0. What if this A is a 3 by 3 matrix? Then your identity matrix must be in 3 by 3 matrix form. Just write your 1 diagonally in 3 places and fill the rest with zeros. So this is how it's going to be for the identity matrix of 3 by 3. But for 2 by 2, this is how it looks like. So you need to solve out, you need to try to find the characteristics equation of this. Find the determinant of this guy here, and then you need to find the values of what? Of lambda. So the characteristics equation is always given as thus, such that after simplifying and breaking it down, you usually get an answer for eigenvalues. Let's say after getting an eigenvalues of 1 or 2, after getting these values, you still need to substitute it back into this part, into this expression here. Let's say lambda is 1. When lambda is 1, then you have a minus 1I is equals to what? 0. So you will have to express this thing again and then break it down to get eigenvectors. So this particular algorithm here shows the step-by-steps to follow in order for us to derive the values for the correct answer for the eigenvalues and eigenvectors. And after that, we have the proof of relevant theorem, which I have actually explained earlier. The proofs are well stated in this case. Trivially looking at what we have here, in this case now, this is the characteristics polynomial, and we want to show that lambda I of minus A is also equivalent to lambda I minus another matrix B. So the proof is well stated from here to here. How will you prove this? This is the proof here, such that in this case, looking at this, what we want to prove, A is equals to B, right? So for A to be equals to B, you need to show something such that A will now be equals to, introduce X times X inverse. Okay, X times X inverse. If X is a matrix and you have the inverse of X, that's surely an identity matrix. If you multiply it by B, you also have B back. Okay, so this A and this expression here are still the same thing. Since A is equals to B, whatever we want to prove, so A is also equals to what? X inverse times X, which is still identity matrix, times B is still B. So it's still the same thing. Then I think in this case too, we did the same thing here. We multiplied this particular term here by X inverse and X. Okay, and then from there, X inverse is common. Factor it out. You have lambda I left. You have X outside. You have B inside. You have X outside. So X inverse is this. You have lambda I minus B. Then you have your X here. So the determinant of X inverse can be written as 1 over X, right? And that's the determinant of 1 over determinant of X. And what's the determinant of 1? That's 1 over determinant of X. So that's how they got this expression here. So this determinant of X here, this one here, we surely cancel the down part. Hence, you have lambda I minus b. So that's well proved. So in this case here, you are trying to find the product of two matrices. How do you multiply matrices together? X and M. Multiply this matrix and this matrix together. See it here. So is that this zero is a square matrix. Let's just say it's a zero matrix, which is 2 by 2. But this one can be any other one, like 2 by 3. This is not a square matrix, n by n. So when you now multiply this and this together, IB 0I, IB 0I, and this one 0 A AAB. If I want to multiply this matrix IB 1 and 0A 0AB, this will multiply this while you had them. I times 0 is 0 plus B times A is what? Is BA. 0 plus BA is BA. That's how they got this result. The same thing goes with this and this. I times 0 is 0. B times AB. That's BAB. You had them. So when you add this, you have this result. So the same thing goes with this too. NX is also the same thing. You now notice that the result for this XM and the result for this NS will always be the same. That's just whatever this one is trying to say. If there's time for you to show the proof, you can show it for you, but you don't really need to show anything. Don't show the theorem at all. Just let them know that the theorem that you brought in this theoretical framework, the theorem you introduced in this theoretical framework here, like this theorem 2.1, like this theorem 2.3, the proof is well stated in section 3, and also for this one too, is well stated in section 3, and also for this similar matrix is also well stated in what? I think I proved this first one, this second one, and I think I proved this one, this 2.4. Yeah, that's what I proved. So now the major aspect is these examples you want to show. Okay, I think this is a continuation of that proof, but you need to explain this thing clearly to them. We have this 2 by 2 matrix according to these are main objectives